All right, so we're going to talk about scaling. I want to have this nice little interlude here. I don't know if you can see this. There's sound probably. Haha. So my, that's just weird. So my, if you go to Farrell, you'll see like, oh, I've got to get that bubble out. Gonna iron this out. So my daughter Charlotte came in and we put that up last night. So there are all sorts of little funny thematic decals now in Farrell Hall. So it's nice. Oh, and this is where we are now. All right, well, Pratchett helped. I'll get to that in a second. He's being a nuisance there, obviously. Best kind of nuisance. All right, scaling. Okay, so this is a whole big section here. As you can see, we're going to go through a bunch of things. Lots of systems have scaling in them. Certainly won't go through all this today, but it's going to we're going to talk about allometric scaling just to start with, just this concept, and then this sort of ranging through a whole bunch of fields, and some may be more than others. This will be about Lego sets at the end, and ant colonies and organizations. All right. Okay, Pratchett, good work. This is really important, obviously. So, scaling, huge. So I could do this all day. All right. I showed it to Charlotte, and she's like, I said, it only took 400,000 goes. All right, so lots of many complex systems, especially when they cross many scales usually. Not always, but they can cross many scales, right? I mean, we could have, usually there's a micro and macro aspect, right? So you've got the individual interacting parts and there's some global thing, but you can certainly have many scales. So this is a thread through lots of different fields and systems. There'll be a second piece after this, which will be more specifically about power law size distributions, which is the probability, for example, if you randomly select a person from the US, how much wealth do they have, right? What's that like? Like very rarely will you get Bill Gates. Or is it Bezos? Is number one, right? And it's like earthquakes, for example, right? So most of the time, not much happens, and then occasionally, bigger things, and then occasionally much bigger things. But that's the next piece. So we're going to talk about scaling. It's usually about how aspects of a system relate. Right. Okay. So basic things, and then in the next course we will do other things. There's a lot of arguing about how you measure these exponents or these relationships. It's quite crazy. 100 years of madness, and then there's some nice pieces in here about branching networks, and I'll touch on this. So I know we've had one person in complex networks, because usually go the other way around, but I have a long piece in there about scaling in biology. So we'll just touch on that. So usually this is a very simple thing. This is it. So here's our first equation. Y equals some constant times x to the alpha. So we've got to get the right terms sorted out. So we'll talk about a scaling exponent or just an exponent. Right, this is the language. This can be any number, of course. So if it's negative, then we've got some decay. Positive, we've got some growth in some way. If it's 1, then you'll have what we'll call isometry. And if it's not 1, then there's some allometric kind of aspect. Depends what we're doing. All right. So this can matter a lot, the prefactor. This is often, and we'll get back to that with Buckingham pi theorem, which is a beautiful piece. It will have to carry, and that's what the next piece here, will have to carry dimensions, right? So this is a really important aspect of equations. So that's okay, I can move forward. So it must balance dimensions. So this is an important thing, we'll come back to it. So imagine we've got some set of objects where the length of them in some, measured in some way, we've got length, breadth, and height, say, length, width, and height. We've got a bunch of boxes at UPS, and they scale allometrically. They're not the same, right? So this this is volume, this would be V to the 1/3 if they were just a bunch of boxes. They don't have to be cubes, right? If they were just rectangular boxes that when you scale them up uniformly in every dimension, they all look the same. But if you have to scale one dimension in a slightly faster way or slower way, and consequently true in the others, then this exponent will start to move away from, has to be different to 1/3. Does this make sense? So it's a little slow. So you can imagine a set of trees, for example, right? So you've got all these trees, and because of the way gravity works, I'm not necessarily saying this is the way trees work. We've got all these trees, we'll have a picture of it, where if we line them all up and then we try to just like, just with like a pinch, right, on a phone or whatever, we're just gonna shrink them and then match them up. Then we see that once we've got them all with the same height, right, we've got these big sequoias and then we're shrinking them down and matching them all up, then they don't have the same widths, right? They're not isometrically the same. They're not just zoomed in or zoomed out photos of each other. So when that's true, when they're not just zoomed in or zoomed out, then we talk about allometry, and I have that in the next few slides. All right, so this is just an example. So this is just a convention here. We'll put these sort of square brackets around, and we'll say this is the dimensions of this prefactor C, right? So it's going to be the dimensions of L divided by the dimensions of volume to 1/4. This is a length scale, so that's what this means. It's a length. This is volume is L cubed, so it's L cubed to the 4th, and so this is L to the 4th. So this carries something, right? So if this was in feet, and this is feet cubed to the power of 1/4, then this has to have a feet to the 1/4 sitting in there. Fair enough? I just want to make sure that's there, because you will see in a lot of things, and we'll start to do this, you put a little tilde here and get carried away and just ignore that and just say they're kind of the same. Physicists do bad things with backs of envelopes, which are prehistoric technology, but I will still refer to them. All right, so that's just a good thing to just kind of have there, right? So the Buckingham pi theorem is coming. That's a great thing. Okay, so very simple thing. In log-log space, these relationships are linear, right? So basic properties of logs. We'll take some base B here, just log of the left-hand side, log of the right-hand side. This is our prefactor. I'll put it over here. Log of a product is the sum of the logs. And then log of x, the alpha, we bring the power down the front. So now we've got log of x and log of y, and this is just a prefactor here. Alpha's become a prefactor. So this is just a simple mx plus c kind of thing. So that seems good. So if we have some power law, whatever it is, x cubed, x3, and we take logs of the data, then we'd like to see that stack up on a straight line. So it's going to actually be a lot of straight, measuring, doing regression on straight lines. So you'd think that shouldn't be too hard. Scientists should be able to work that out. It turns out there are many ways to do regression. And there's actually one good way. There's actually only one way that doesn't involve the dimensions, right? So x and y, right? This could be money and happiness. They're measured in different ways. So there's only one that sort of deals with that properly. Or I should say, it doesn't matter if you change units, right? Right. Okay, so there's a lot of messing around, as I said, with looking for straight lines on these double logarithmic plots or log-log plots. People just sort of say this. Now, we're humans, we've got the 10 thing going on. This is just what happened. We talk about log 10. I know if you're a pure math person and you want natural logs, that's fine. But it's just, this is being good social humans, right? This is what lots of people have done over time, and we've kind of just got in our head. So when we talk about, yes, the dozenless would be better, but we have failed them. Aliens will appear and say, what are you doing? What's going to happen? These idiots use 10. I mean, there'll be other things they'll laugh at, but anyway, but hands, right, and social pressure. So we're on the 10 thing. The French kind of won this one, but 12 really would be good, or whatever, 60, Sumerians, I think they're into 60s. Okay, so, but this is what we're going to do. And you have to label it. You have to put log 10. I'm just going to say this. You see papers and they don't, and you're like, what is going on? That's not right, right? Be good people. So this is being good people. So it's possible that this is an accident. The hands thing, the whole 10 digits business is an accident of history. But that's debated. There are some efforts to explain that it makes sense from a growing, things growing on the ends of arms point of view. Josh Bongard, I guess, is going to sort that out for us. But it does feel a little whatever. And of course, when we make aliens for, TV or whatever, they usually have different numbers of digits. And The Simpsons, right? Just 3 plus 1, yeah. Okay. Okay. So we're going to talk about orders of magnitude means powers of 10, right? Carl Sagan put this into a whole generation, but that's a long time ago.